So we're on to section C now, which is all of the multi-choice. So I'm going to go through these reasonably quickly. A nucleus of an element decays with alpha and beta minus, which are the following emissions. So if we have an alpha, we lose 2 protons. We need an isotope of the original element. Every beta, we gain a proton. So we lose 2, gain 2. So that would give us back to the original element here. Which of the following shows a process of annihilation? So we need to have a particle and antiparticle meeting. So that's a particle and antiparticle, that's a particle and antiparticle meeting. No, that's not a particle and antiparticle because that's a pi naught. So it's definitely not that one, but it wouldn't work anyway because you need 2 those, but that's the one there. Particle and antiparticle releasing 2 gamma photons. Which of the following is not made of quarks? So we're looking here for the lepton. That's a baryon. That's a hadron. That's a hadron. So it's the muon, which is related to the electron. It's the bigger version of the electron. What's the quark structure of an antiproton? Well, a proton is up, up, down. So an antiproton is anti-up, anti-up, anti-down. This question here was not required to be answered because it's a silly question. Question 10, we are looking for some jumps. So 3 to 1, that gives off visible light. So if that gives off visible light, we're looking for a jump which has more energy than that to be ultraviolet. Ultraviolet's got more energy than visible light. So that's less energy, that jump there, so it's not that one. 3 to 2, that's definitely less than that one. 2 to 1, that's definitely less than that one, because those 2 add up to that one. 1 to 0, that's probably more than that one, and you can check by looking at the numbers, the difference in that number and that one number, and the difference in that number and that one number. Well, that's about 10 electron volts apart, that's about 2.5, so it's definitely that jump there. This is not drawn to scale. Just be careful about things like that when they're not drawn to scale. The proton moving with speed v has de Broglie wavelength lambda. What about an alpha particle moving the same speed? Well, an alpha particle is 2 protons, 2 neutrons, so it's got a mass of 4 times as much. If it's got a mass of 4 times as much, the same speed, then its momentum is going to be 4 mv, whereas the previous one was mv. So its de Broglie wavelength will be 1/4 of its original value because its momentum is 4 times. What's the phase difference between 2 points 0.6 meters apart on a progressive wave? Okay, so this one, first of all, there's quite a few steps in this one. We need to do v is equal to f lambda to work out what the wavelength of this is. So we've got 330 divided by the frequency of 256, which is about middle C, I think. So 330 divided by 256, oh, that's wrong. That's wrong. So we've got 1.289 meters. Right, now what we need to do is find out what fraction that much is. So that is 1.29, 29 meters. It's about 1.3 meters, isn't it? So how much is that of that? So we need to do 0.16 divided into our answer, which gives us, so we are 0.12 along, so that's essentially about 12.4% along. If that is 2 pi, I want to know how many pi's this is, so I times that by 2, and we're pretty much on 1/4 there, aren't we? So it's 1/4 pi along there. So that is pi by 4, which is that one. Okay, so what did I do there? I worked out the wavelength. I equated that to 2 pi for a complete wave. I worked out what proportion that is of the total wavelength, and I've figured that my answer here must be the same proportion of 2 pi that is of 0.16 meters is of the total wavelength there. So a little bit confusing, but not too hard in the end. This one here, we've got the wavelength on along a wire, so it's using this first harmonic equation here. So F is proportional to root of T, the tension, divided by L, all the rest are remaining constants, of course. So if we double both, we're going to have F prime is equal to the original F. We're doubling tension, so we've got root 2 over there, and we're also doubling the length. So we've got 2 over there, which is root 2 over root 2 times by root 2. They cancel, so it's the old frequency divided by root 2, which is that one there. Question 14. In a diffraction grating, maxima are produced on a screen. What causes separation of the maxima to decrease? Using longer wavelength, that will cause them to increase. Let me just show you the equation for this diffraction grating here. So the separation of the maxima is essentially that sine theta there. So that will make that bigger. Increasing the distance between the screen and the grating, again, that will make them spread out more. If you have your lines like so, if you put the screen here and you put the screen here, if you make that distance longer, then you can see that those are more spaced out than those were. So that's not it. Increasing the distance between the source and the grating, that will have virtually no effect. Using a grating with a greater slit separation, well, to make them spread out more, you want the slits to be closer together. So greater slit separation means that they are not as separated out. So it's that one. White lights pass through a single narrow slit, illuminates the screen. What is observed? You need to know this pattern off by heart. Nope. The central maximum made up of a spectrum. Nope, central maximum is white. So central maximum is white, surrounded by coloured fringes, that's it. A single narrow white line, no, you wouldn't see that. You'd see white in the middle, and then a spectrum on the outside going to red near the outside, and then you'll see a funny spectra coming out the other way as the colours all merge with one another in different ways. Which of the following is correct when total internal reflection occurs? The angle of incidence is less than, no, it's more than the critical angle, so it's not that one. Light meets an optically less dense medium. Yes, that's correct. You start in glass, end up in air, for instance. So that would be the one. Light enters a medium with a higher refractive index. No, it's the opposite way around. And the angles that they make with you don't have any refracted rays because you're total internal reflection. What's the speed of light refractive index of 1.42? You pretty much guess this one is B, but let's do it properly. So you need 3 times 10 to the 8. You divide by the refractive index to find the new speed of light. So that is that one there. What's the scalar quantity? So that's got direction because it's got velocity. That's got direction because it's a force. That one has no direction because it's made up of energy and time. That one has direction clockwise or anti-clockwise. Question 19. Velocity time graph here, and we need to find the corresponding acceleration graph. So to get acceleration from velocity time graph, it's the gradient. So there the gradient is big, so we need something that starts with a gradient big, so that one or that one. There the gradient gets smaller and smaller, so it has to be this one because that one's the acceleration is constant. So it's got to be B. Girl jogs at 2 meters per second as a straight line for 30 seconds. So what's that? That's a total of 60 meters, isn't it? Turns around and returns to a starting point 20 seconds later. So on the right. What's our average velocity and our average speed? Well, average velocity she has ended at the same place that she started, so her total displacement 0. So it's either that one or it's that one. Then we just need to work out her average speed. So she's done a total of 120 meters, and she's done it in 30 seconds plus 20 seconds, 50 seconds, which is 2.4, isn't it? So it's that one. So it's got to be A. Golf ball hit from the surface of the moon, flight time was 4 seconds. Oops, that's dreadful. There we go. So T equals 4 seconds. What's the best estimate for the maximum height reached by the ball there? So this is a projectiles question. You can use S equals UT plus a half AT squared. We know that if it takes 4 seconds to get to there, it's going to take 2 seconds to get halfway. So T is equal to 2. So T height H. So here goes. Vertically. Right. Okay, let me have another go at explaining this. You can do this in multiple ways, but the easiest way to do it is just to consider the second half of the journey here. If you consider the second half, then when it goes up here, it's in the vertical plane. Its final velocity, or its velocity at the very top vertically is 0. It's not going up and it's not going down. It's just about to accelerate down. So we can have U is equal to 0. There is an alternative version of this which has V instead of a T there, but it's not on the formula sheet, so it's slightly different. But essentially we can have therefore that U is equal to 0. So we have S is equal to 0 times by T plus a half times by the acceleration, which is 1.6, times by T squared, and we're doing half the journey from the top to the bottom is 2 seconds. So it's 2 squared. So that's half cancels with one of those 2's. We've got 3.2. So it's 3.2 meters. So it's that one there. A deep space probe travelling at constant speed is briefly acted upon by so it's moving like that. It's acted upon by a force on the side. What effect will this have? It will have no effect on its velocity in that direction. Instead, it will introduce a new component of velocity in that direction. So its resultant velocity will indeed be in that direction. So its forward speed increases. No, it doesn't. It stays the same. Its forward speed decreases. It stays the same. Forward speed is unchanged, so we're good. The sideways speed increases. Yes, it does. So that one's true. Forward speed decreases. No, it's got to be that one there. The mass of fuel in a racing car decreases during a race. As a result, the lap time decreases. So the car's essentially getting less massive. So which of the following could explain this decrease? There's less friction on the racetrack. Well, yes, there would be, but that's not going to improve lap times. It would actually make it worse. You need grip. The maximum speed of the car has increased. I don't see why, maybe. Who knows? Probably not. The maximum acceleration and deceleration are greater. Yes, because look, F is equal to ma. So if we say that we can generate the same amount of force, no matter how much fuel is in the car, but if the mass is lower, then the acceleration will be bigger. The same with braking as well. So that's why it can accelerate and decelerate more rapidly. The engine is more efficient. That makes no sense. What is represented by the area under a force displacement graph? Well, force times by distance is work done. So it's definitely that one. Which of the following is not a unit of power? Well, joules per second is a unit of power, so that one's definitely not a unit of power. So we can shortcut to the answer there without looking at any of those. A roller coaster car is raised to a height of 65 meters and released from rest. What's the maximum possible speed of the car? I assume it doesn't go underground. So there we have 65 meters. So we can apply, you can either do this with energy or you can do this with SUVAT. I'm going to do SUVAT. So S equals UT plus a half AT squared is not the equation I want to use. I want to use V squared equals U squared plus 2AS. Because I want to find the final velocity. Initial velocity is 0, so V squared is equal to 2AS. So we've got 2 times by the acceleration of gravity, 9.81, times by the displacement, 65, and we need to square root that answer, and we get 36 meters per second, which is that one. Could also do that with energy. mg delta h is equal to a half mv squared. The mass of the carriage cancels out, and you, lo and behold, get the exact same equation that you've got there. In a test, a 500 kilogram car is traveling at 10 meters per second, hits the wall. The front 0.30 meters of the car crumples as the car is brought to rest. What's the average force during the impact? There's quite a few things to do here. Well, firstly, we're going to use this equation, Newton's second law. So that's going to tell us the force. So we need to first of all find the change in momentum, but we also need to find the time. So the change in momentum is going to equal the final velocity, which is 0, minus the start velocity, times by 500, so that's equal to minus 5,000 kilogram meters per second. So that's the change in momentum. It's reduced by that much. Now we need to find out the time for the collision. We're actually told the displacement. So if this is the velocity here of the truck or whatever it is, and that is the time there, then the area under this graph is equal to the displacement. The velocity starts at 10 meters per second, ends up at 0. This is equal to 0, and this is equal to whatever t is, and that's equal to 0.30 meters. Okay, so the equation for this is S equals U plus V over 2, the average velocity times by time. So we're assuming that it decelerates at a constant rate for this. So S is equal to 10 divided by 2 times by t. Oh, S was actually given. So we've got 0.30 is equal to that. So that means that t is equal to 0.6 divided by 10, so that's 0.06 seconds. So then we need to do our momentum change divided by our time. So we've got 5,000 divided by 0.06, 5,000 divided by 0.06, just interested in the size here, so it's 83,000. So it's that one. So there's lots to do in that question. The current of a wire is 20 milliamps. How many electrons pass a point in 2 minutes? So Q is equal to I times by T. So that's 20 times 10 to the minus 3 times by 2 minutes times by 60 to turn that into seconds. So we have 20 times by 120. So that's how many coulombs you've got. Then you need to divide that by the charge on an electron. So the number of E is equal to Q divided by the charge on an electron. So that's 1.6 times 10 to the minus 19. Gives you 1.5 times 10 to the 19. That one. Question 29. We're going to have this, we're going to increase the potential difference across here and see what happens to the current. Well, what's going to happen is once the potential difference is below the conductance, the voltage drop required to make this conduct, no current will flow. So we've got to have no current flowing initially, so it's either that one or that one. And then once we get to, it's about 0.6 volts across there, this will start to conduct electricity, and so therefore the resistor will take up the rest of the potential, and it'll just, the current's proportional to the potential difference. So it's this one, it's got a straight line there. So that's when the diode's off, that's when the diode turns on, starts to conduct as much electricity as you like, much current as you like. There, so it's A. Question 30. A cell of negligible resistance and a switcher in series with a resistor. The switch is moved to the on closed position for time t. Which change reduces the amount of charge flowing through R in a time t? So the amount of charge flowing in a time t is the current. So it reduces the current, is what we're after. Okay, so adding another cell in parallel, that will do nothing. Adding an identical cell in series, well, assuming they're putting it the same way round, that will increase the flow of current. Adding a second resistor in series, that increases the total resistance of the circuit, so it reduces the current, so that's the one. Adding a second resistor in parallel will reduce the resistance, so that won't change it. That will make it actually, well, it won't change it through R. The total current flowing will change. The national grid uses high voltage transmission lines. A particular transmission line delivers that much power at that voltage to the user and loses 1% of the transmitted power as heat. Okay, what's the resistance of the line? Well, first of all, we need to work out how much power is wasted. So the power wasted is equal to 1% of that, which is 8 times 10 to the 6 watts. Okay, then we need to, so that's the power that's wasted. Separately, we need to work out the current that's flowing in the wire. Because although the voltage of the delivery is that, lots of people get confused here. That's not the voltage drop across the wire, that's the potential of the wire compared with ground or compared with neutral. So we need to find the current flowing through the wire, and to do that we just do P equals I times by V. So I is equal to P over V, which is equal to the total power delivered, 800 times 10 to the 6, divided by 132, and that's 1,000 because it's kilovolts there. So we've got 800 to the power 6 divided by 132 to the power 3 gives us a current of 6060 amps. Right, then we can use P wasted is equal to I squared R. So R is equal to P wasted divided by I squared. So that's equal to the power wasted was 1% of that, which was that one, 8 times 10 to the 6, divided by I squared, 6060 squared. So we need to square that, and we do 8 million divided by that answer is 0.2 ohms. There. Okay, potential divider, question 32, consists of a battery connected across a thermistor and a variable resistor in series. Thermistor, variable resistor in series. So that's our V out across there. Which of the following causes potential difference across the thermistor to increase? Oh, sorry. So we want this one. Potential difference across the thermistor to increase. Increasing the temperature of the thermistor. That won't work because temperature and resistance do that. So we'll reduce the resistance to that, so we'll have lower voltage across that. Increasing the resistance of the variable resistor, that will make that have a greater share of the potential, so that will have a smaller share. Reducing the EMF of the battery will proportionally reduce both of them, so that won't work. So it must be this one, adding a resistor across the variable resistor. Well, if we do that, then we reduce this resistance because we've added something in parallel. So that means that that voltage will drop, and so that one must increase. So they both add up to the supply there. So it's that one. Student investigates how the potential difference across the terminals of a cell varies with the current in the cell. Which graph correctly shows how V varies with I? Well, when you're drawing no current, V is equal to the EMF. So it's got to start at a positive value. So that's the only one that starts at a positive value. And then as you draw more current, you get more lost volts. So the potential across the terminals drops. So it's definitely that one. Question 34. Battery is connected to a 10 ohm resistor and a switch in series. So battery, 10 ohm resistor, switch. Okay. The voltmeter is connected across the battery. When the switch is open, the voltmeter reads 1.45, so that means that the EMF is equal to 1.45 volts, because when no current's being drawn, that's the EMF. When the switch is closed, it's 1.26 volts. Okay, so what's the internal resistance of the battery? So we need the EMF is equal to I times, but that's big R there, so we want a little resistor there as well, don't we? Plus I times by little r there. So we can work out what the current flowing when the switch is closed is. So I is going to equal V over R, which is equal to the potential difference across there, which is 1.26 divided by resistance there, 10, so that's 0.126 amps. And then we know everything else in this. We know that, we know that, we know that, and we don't know that. So we've got 1.45 is equal to 0.26 times by R is just the original EMF, plus 0.126 times by little r. So we have 1.45, take that away, 0.26, so that's little r, it's equal to 1.45, take away 1.26, divided by 0.126, divided by 0.126, gives us 1.5 ohms. And that is the end of paper 2. I hope you found that useful. If you did, please share it with your colleagues at school and your teachers, and good luck in your exams.